you later. After we finish building the full adder, you can make a very important observation out of it. So yeah, so how many inputs do we need for a full adder? We need 3 inputs. So first let's take 3 inputs. So
After
I'll give an intro to all
building
the
the
tools
full
out
adder,
here.
you can make a very
This is the
important
hand tool.
observation
This
out
is
of it.
used for switching.
So
This is
how
used
many
for
inputs do we need for a full adder? We need 3 inputs. So first let's
this is used for switching
3
inputs. So
after
I'll
we
give an
finish
intro to
building
all
the
the
circuit
tools
over
something
here,
like this.
you can make
You
a
can
very
switch the
important hand tool.
inputs
This is
by
used for
using this
switching.
hand icon. Okay. So
This is used
it
for
switches from
we
0
need
to
for a
1,
full
1 to
adder.
0, and so
We
on.
need 3 inputs.
This is the cursor. This is
So
basically how you do
first
the wiring.
let's
You place all the logic gates and all that.
after we finish
And
building
this
the
is
circuit
wiring.
over
You
here,
can do it specifically
you
if you
can
want.
switch the
Otherwise, you
hand
could
tool. This is used for
just
hand icon.
drag from here and just drop it.
This is used
it
for
switches from 0 to 1, 1 to 0,
and
and this is the text one. Like it's obvious. These are the this is the input terminal kind of thing, and this is for output. Yeah, and these are the basic gates that we use very often: NOT, AND, OR, XOR, NAND, NOR, and all that. And if you want any other gates, or if you want any other advanced like things that you don't have to build it from the scratch, you can directly use them from here. You have so many plexes, arithmetic operation performers like adders, subtractors, multipliers, etc. available here. You have memory elements like flip-flops and registers here. So yeah, so you have pretty much everything that you want to build a circuit using. And yeah, let's go on with our full adder circuit. So we had our expression for sum as A XOR B XOR C, or like X XOR Y XOR Z, and the expression for the sum as AB plus CN into A XOR B, which is nothing but XY plus Z into A XOR B. So we need 3 inputs first. So let's start with 3 inputs. So there's another shortcut key to bring these inputs. That's nothing but Control+5. Control+5, just like it's kind of useful to build circuits fast. And yeah, if you feel like your workspace is zoomed out so much, you can zoom in or zoom out here at the bottom left. So I feel 2 is comfortable. And now we bring XOR gate. Now we need another XOR gate. So and Control+C is the shortcut for output. So if like you don't have to remember these shortcuts, you can bring it from here directly. And yeah, I like to label all my input terminals. So you click on the input, and then here you have label, like all the information given about that component that you're using. So under label, you can label it as A. And then here, you can label it as B. This you can label it as C. Okay, so the output here will be nothing but A. Okay. Oh, wait. We'll do all that at the end. So yeah, we got the sum. Now we need to build the circuit for output carry. So how do we do that? I told that this expression is going to be quite useful for building logic circuit. XY plus Z into X XOR Y. right? So we are going to use this expression for finding out the carry output. Why? Because we already have X XOR Y in our circuit. So it will try to make the circuit as small as possible by using this expression. So yeah, we need A and B. So we take AND gate, give inputs from A and B. And we have, we need another AND gate, which takes input from A XOR B and C. Now I'm going to combine the outputs from these two gates using an OR gate. So this is nothing but the carry output. Okay, so we can check whether our circuit is correct or not by using the hand icon. You can give the inputs here. So what happens when A is 1, B is 0, C is 0? Sum is 1, carries 0. What happens when A and B are 1? Sum should be 0, carry should be 1. What happens when A, B, and C, all of them are simultaneously 1? Both sum and carry output should be equal to 1. So I hope you guys were doing along with me. I'll wait for some time for you guys to complete. And yeah. If there is any difficulty, please let me know. Is there any part that I have to repeat, like that you guys are struggling to build the circuit? And there is nothing but A and B. How to select the input and output? You just click on, okay. So this is the input. Okay, this is the workspace getting zoomed in. At the top, you can see so many icons out here. So this is the input, the pentagon shape. And like this is the input and this is the output. So you can just click that, drag and drop wherever you want. And if you want to alter some properties of the component that you're using, you can do it here. You have label, you can name the component, and like for gates like these, logic gate, you can alter the number of inputs that it takes here. Like you can make it take 3 inputs, something like that, 3 or 5, as many as you want. So you can see this output is nothing but A XOR B. So the problem here is I can't write the XOR tool here. So I'm just writing it in words. A XOR B. And here what you have is C into A XOR B. Right? And the output here, what you have is A XOR B XOR C. And so, yeah, and there's another feature that you can see in Logism. So once you build the circuit, you can go to project and you have this analyze circuit option at the end. Okay, third from the bottom, you can click that. And so you'll get this combinational analysis, which will show you the truth table itself. You can also see the expression here, expression for sum. Okay, I'll keep the box somewhere here. So you can see the expression for sum and the carry output. You can also find the K-map yourself here. So for the reducing the expression of S, this is the K-map that you have. This was the checkboard configuration that I was telling you about. You can get the K-map both in sum of products as well as product of sums form. Again, you can change the output and you can see the K-map for output carry as well, both in sum of product as well as product of sum form. So you can change the number of inputs and outputs you get, inputs and outputs you want, and you can like change the truth table here. Like, yeah, you can edit the truth table here, and by editing the truth table, you can once you give build circuit, it will build the circuit on its own. You don't have to build the circuit yourself. All Logism requires is a truth table and the number of inputs and outputs you want. So that's a very good feature in Logism. You can try it out later. So yeah, those icons are visible for me for input. Are you guys facing any issues with input and output? I've attached the circuit, the circuits, final circuits image also, so you can refer it and do it, finish it off later. I'll attach it with the slides. Now there's one thing that you can observe here is that a full adder circuit is nothing but a combination of two half adders put together with an OR gate. So this together, one XOR gate and one AND gate together makes up one half adder. This XOR gate and AND gate together makes up another half adder. So when you put these two half adders together with an OR gate, you get a full adder. So that is why, in fact, they were named like that as well. And yeah, let's keep going. We'll move on with binary adder. Binary adder is basically, it's a digital circuit that produces the arithmetic sum of two binary numbers. It is constructed by cascading full adders one after the other. And addition, this is something that you have to note, and this is intuitive as well. Addition of n bit and numbers requires a chain of n full adders. Now, a binary adder basically adds two n-bit binary numbers. A full adder can add only 3-bit numbers at a time. So what we do is to add two n-bit binary numbers, we put many full adders like in a cascade. Cascade in the sense one after the other in a series way. And so let's take the full adder. The first full adder takes in its inputs as the first bit of the first binary number and the first bit of the second binary number. So let's take the two binary numbers that we are considering are an minus 1 till like a3, a2, a1, a0, and the second binary number is bn minus 1, bn minus 2, it goes on till b3, b2, b1, b0. So this is nothing but A0 will be the first bit of the first binary number and B0 will be the first bit of the second binary number. A1 will be the second bit of the first binary number. B1 will be the second bit of the second binary number, and the same pattern repeats. So we take the first bit of the two binary numbers and we add them together. And we first take this, the third bit that we are going to take for the full adder as 0. Input carry, we are going to assume it as 0. And then we add these three numbers, the usual truth table that we have for full adder. The outputs that we get are a sum S0 and carry C1. So the sum 0 will be the first bit of our final sum. Okay. Now this carry 1 is taken as the carry from the first full adder is taken as the input to the next full adder, and the next full adder takes inputs as the second bits of the two binary numbers that we are going to add, A1 and B1, and it also takes the third bit as the input, the carry from the previous full adder. So that is why this is called as the input carry. So the carry from one full adder, output carry from one full adder is taken as the input carry for the next connected full adder, and the process repeats again and again. So whatever is the sum of the second full adder, it will be the second bit of the final sum, and the carry it gives goes as the input carry for the next third full adder. So the same procedure repeats till the end. So finally, this is an image of a 4-bit adder. When you add two 4-bit binary numbers, you can get the final sum as 4 bits, or it could be 5 bits. Why it could be 5 bits? It's because the carry that you get from the last full adder, you write that as well. So the final answer will be C4, S3, S2, S1, S0. That will be the final sum that you get. So a 4-bit adder could give a sum that is either 4 bits or 5 bits. So I'll repeat binary adder again. A full adder can add only 3-bit numbers. So we take the first bit of the first number and corresponding first bit of the second number, and then also the past generated carry. So that carry for the first case is 0. After the first case, for every case after that, this carry is nothing but the carry generated by the previous full adder. And then we take these three inputs, we add, we get a sum and a carry, we pass on the carry to the next full adder. The process repeats till we finish the addition for all the bits of the binary number. So obviously for n to perform the addition of n bit numbers, then we need n full adders, because we are actually in each full adder performs the addition of each bit from both the both the binary numbers. So you'll need n full adders to complete the addition of each and every bit of that n bit binary number. So the carry output of each full adder is given as input to the next connected full adder. That is all about binary adder. Okay. And here's an example. Let's take these two binary numbers. A is equal to 1011 and B is equal to 0011. So these are the two binary numbers. So let's start from the least significant bit. So here we are going to take the first input carry as 0. We're going to add 1 and 1. When we add 1 and 1, we get sum 0, carry, output carry 1. We take this output carry as the carry input. Input carry for the next full adder. Okay. Then we add these 3 bits together. What do we get? 3. How do you 1 plus 1 plus 1? you would have seen already. It is nothing but sum is 1, carry is 1, right? 1, 1, 1, sum is 1, carry is 1. So same thing happens here. Now this output carry is taken as the input carry for the next full adder. And yeah, sum is 1, carry 0. Take this to the next full adder. Sum is 1, carry 0. So this is the final sum that you get. 1, 1, 1, 0. And sometimes you may get a carry here as 1. In that case, your final sum will be that 1 also taken into consideration, and you will get a 5-bit number as your final sum. If it is 0, then it's just if the output carry, final output carry is 0, then it's just a 4-bit number. So this is how a binary adder actually works, like the addition of two binary numbers actually works. And is there any doubt in this? Let me check. You're unable to find full adder. Okay, full adder is something that you're gonna build. You have to create a new circuit here, write full adder, and then if you click OK, you will get a new workspace. Full adder, you can also get it as a separate thing here, adder, and just like full adder is nothing but a binary adder with which is adding just two binary, which is adding two 1-bit binary numbers, right? So that's how you get a full adder directly, like by default. Yeah, let's proceed with half subtractor. Half subtractor is very, very identical to the half adder that we learned. So the only difference in this logic circuit also you can see is that there's a NOT gate out here. Half adder does not have this NOT gate. That's it. And again, it takes two it takes two inputs A and B and gives out the two outputs, difference and borrow. Okay, so this is the truth table. When A and B are 0, difference is 0, borrow is 0. When A is 0, B is 1, difference is 1, borrow is 1. Why does this happen? I give you the like you cannot subtract 1 from 0, right? So why do we get these outputs? I'll explain you how using this example. So let's take your let's assume we are going to subtract 0, 1 from 1, 0 in binary, okay? So you can't subtract 1 from 0. What do? You take carry from the next digit, okay? You strike out this 1, you make it as 0. This is nothing but 2, like it is very similar to decimal subtraction. So just first assume this. How do you write 1, 0? 1, 0 is nothing but 1 into 2 power 1 plus 0 into 2 power 0, right? 1, 0 is nothing but 1 into 2 power 1 plus 0 into 2 power 0. Similarly, 0, 1 is nothing but 0 into 2 power 1 plus 1 into 2 power 0. So when you strike off this 1 and you get, when you take a carry from the next digit, you're actually bringing in a value of 2 from the next digit to the single digit. So it's similar to how you do, like if you it's similar to decimal subtraction. So if you're subtracting say 8 from 10, what do? Like directly you can say it's 2, but what actually happens is you take off the decimal digit 1 and you make 0 as 10, and then you subtract 2 from 10 and you write you subtract 8 from 10 and you write 2, right? The carry is nothing but the weight of the next digit coming to this digit, a less significant digit. So this is nothing but this 0 now becomes 2. So 2 minus 1, you get the difference is 1, and you took a carry as 1. You not a carry, borrow, sorry, not a carry, borrow. So you took the borrow as 1. So that is why when you subtract 1 from 0, the difference is 1 and borrow is 1. Why? Because when you take a borrow 1, this 0 becomes 2. So and 2 minus 1, difference is 1. Okay, 1 minus 0, difference is 1, borrow is 0, obvious. 1 minus 1, difference is 0, borrow is 0 is also obvious. So this is the half subtractor circuit. Very simple. I'll move on with full subtractor. Full subtractor, it's very similar to full adder. And this is the truth table for full subtractor. You have 3 inputs and 2 outputs, same as in the case of full adder. Here A is called the minuend and B is called as the subtrahend. And you get the outputs as difference and output borrow. So it's the same. I'll just go through the truth table. So I'm starting with the second one. 0 minus 0 is 0. You subtract 1 from 0, you get difference 1, borrow 1, right? Now, let's go with the fourth example. A is 0, B is 1, B input is 1. B input is nothing but borrow input. Like it's the same reason, just like how we named the third input in full adder as carry input. We name the third input in full subtractor as borrow input. Why? Because a very similar procedure will as it was in binary adder, it can be seen in a binary subtractor as well. The borrow input will be moving on to the consecutive full subtractors. So that's why we call this guy as borrow input. So you have 0 minus 1, you will have difference 1, borrow 1, and then you subtract and you have another 1 in B in. So your difference will be 0, B out. You can just go through the truth table. It's quite easy. And yeah, from the truth table, you can write the expression for D and borrow output. Write the min terms each, like which is corresponds to the 1 in these terms, like 1 in this table for each of these variables. You will find you can write these expressions. I guess this is pretty direct now. And you'll get a very similar tables, K-map tables. And yeah, you can again see a checkboard configuration for D and B out. You will have something like this. And checkboard configuration means obviously XOR combination of all the inputs. So D will be A XOR B in. So draw K-map yourself and figure out the expressions. Okay, it's just a task you can try out. So, and you can try to build a full subtractor circuit and logism on your own. This is the final circuit that I've given to you as reference. You can try to build it on your own and just check it out. It's very easy. Again, you can see this is nothing but a half subtractor. This is another half subtractor. This XOR gate, NOT gate, and AND gate put together. And when you put two half subtractor circuits with an OR gate, you get a full subtractor. Okay, so let's move on to magnitude comparators. Basically, what a magnitude comparator does is compares two binary numbers and determines their relative magnitude. So one of these outputs must be true, provided we have two binary numbers, A and B, given as the inputs. So either A should be less than B, or A is equal to B, or A is greater than B. Is there any doubt so far? So the most basic magnitude comparator that you can see is a 1-bit comparator. So 1-bit comparator basically compares two numbers, each of 1 bit. Okay, so you compare 0 and 0, they're equal, A is equal to B gets 1. And then when A is 0, B is 1, B is greater than A, that will have 1. And when A is 1, B is 0, A greater than B has 1. and when both A and B are 1, A is equal to B gets 1. So then figure out the expressions for A greater than B, A less than B, and A equal to B from the truth table. You can see for A greater than B, you have 1. When A is 1, B is 0. So the minterm should be A, B complement. A less than B is 1. When A is 0, B is 1. So the minterm should be A complement B. And A is equal to B is 1 when both A and B are either 0 or 1. So this is nothing but the XNOR gate, A complement B complement plus AB. Okay, so from this you can easily build this logic circuit. It is also pretty direct. Now moving on to a 2-bit comparator. 2-bit comparator, say any n-bit comparator, how it works is it compares 1 bit at a time, starting from the most significant bit and moving on to the least significant bit. So let's say if you're taking a 2-bit comparator, A1, A0 is the first binary number, B1, B0 is the second binary number. So we first compare the most significant bits of the 2 binary numbers, which are A1 and B1. We compare A1 and B1 first. Now, if A1 is greater than B1, we directly say A is greater than B. If A1 is equal to B1, then we move on to comparing the next two bits, which are nothing but A0 and B0. Getting it? So let's see some examples. If you see here, second case, A1 is 0, A0 is 0, B1 is 0, B0 is 1. When you compare A1 and B1, they are equal. Both of them are 0. So we move on to comparing A0 and B0. A0 is 0, B0 is 1. So B0 is greater than A0. Hence B should be greater than A. So A less than B gets 1. Let's go to the third case. A1 is 0, A0 is 0, B1 is 1, B0 is 0. So you can, when you compare A1 and B1, what do you get? You can see that 1 is greater than A1. So directly you can say that B is greater than A, right? So yeah, it's very simple. The same thing applies everywhere. We'll look at the last case. So A1 is 1, A0 is, no, not the last case, the case before the last case. Okay, so A1 is 1, A0 is 1, B1 is 1, B0 is 0. What happens in this case? We compare A1 and B1, both are equal to 1. So we move on to comparing A0, B0. A0 is 1, B0 is 0. So A is greater than B. Hence, that gets 1. So that's all about the truth table. It's very simple. You can construct it. So you can then draw the K-map for output A is equal to B. And this is the kind of K-map that you will get. All the diagonal elements will be 1 and you can't group them with anything else. So you have to take them separately. If you try to write down all these diagonal elements and reduce them, you will get this as your final expression. A0 XNOR, this is the symbol for XNOR, a dot with a circle around. That is the symbol for XNOR. So A is equal to B expression is nothing but A0 XNOR B0 and A1 XNOR B1. Now you can see XNOR is nothing but XNOR is 1 when A and B are equal. Like when both A and B are 0, XNOR is 1, or when both A and B are 1, XNOR is 1. So it actually makes sense, right? So for A to be equal to B, both A1, B1 should be equal and A0, B0 should be equal. A0 XNOR B0 ensures that A0 is equal to B0. A1 XNOR B1 ensures that A1 is equal to B1. So both of them must be simultaneously true. So we have an AND gate in between. Next, you have the K-map for output A greater than B. And it is again very simple. You can make groups and then write down the minterms, reduce it. This is the final expression you get. And K-map for output A less than B, you can try it out yourself. You can draw the K-map yourself. This is just an exercise. These applications are like exercises for your K-map practice. Okay, so K-maps are very, very important in digital design. So the more and more you draw K-maps in practice, the more comfortable you will be with working in digital design. And A less than B, this is the final expression. After drawing the K-map and simplifying, you can check it out. So yeah, let's make a 2-bit comparator in Logism. So since we are in short of time, I've made the 2-bit comparator. I'll explain to you. I have also attached the final circuit here. You can look at it and write out yourself after the session ends, or maybe we'll give it as a task for you, the post-session task. Okay. So by the way, is there any doubt? So we'll finish it off fast. So this is a 2-bit comparator. It has two 1-bit comparators and it takes 4 inputs, as we saw before in the truth table as well. It takes the inputs A1, B1, A0, B0, and one minute. I'm extremely sorry, guys. Yeah, let's continue. So these are two 1-bit comparators. Now, thing is, you can build your own 1-bit comparator if you want. You can go to arithmetic and you have all these comparators built already for you. And you can use them as well. You just take that, click on that comparator and you place it. That's it. Otherwise, you can build your own 1-bit comparator, and you can just click on that and place it. So, for example, here, this is what I built my own full adder, and I can just place it here like that. Okay. So it's up to your wish, but yeah, Logism has some ready-made tools available, and these are the 1-bit comparators. These are the 3 outputs. A1 less than B1, A1 equal to B1, A1 greater than B1, A0 less than B0, A0 equal to B0, and A0 greater than B0. Now, these are the 2 binary numbers that we are going to compare, A1, A0 and B1, B0. So let's finish the equal to case. For P to be equal to Q, A1 should be equal to B1 and A0 should be equal to B0. So we take A1 equal to B1 and A0 equal to B0, and this is nothing but this middle AND gate and this middle output. Now, for P to be less than Q, either A1 should be less than B1, which is nothing but this branch, A1 less than B1, or A0, A1 should be equal to B1, A1 must be equal to B1, and A0 should be less than B0. A0 should be less than B0. I guess it makes sense. A1 should be equal to B1 and A0 should be less than B0, which is nothing but this AND gate and its output. So we put them together in OR combination and we get the final output as P less than Q. Similarly, for P greater than Q, either A1 is greater than B1, which is nothing but this branch, A1 greater than B1, or A1 should be equal to B1 and A0 greater than B0. So A1 equal to B1, which is nothing but this branch, A1 equal to B1 and A0 should be greater than B0. So these are the two inputs for this AND gate, and the final output you get is A1 equal to B1 and A0 greater than B0. So when you put these together, in an OR gate, you get the final output as P greater than Q. So these are the three outputs for a magnitude comparator. And yeah, we can check the outputs, whether our circuit is correct or not, by giving different inputs to it. So yeah, when A1 is 1, which is greater? P should be greater than Q. So yeah, it's right. When B1 is also 1, B should be greater, right? So which means Q should be greater than P, because both B1 and B0 are 1, while only A1 is 1. So Q is greater than P. So when A0 is also 1, P should be equal to Q. So this should be the output. So our circuit is right. Okay. If you want, you can check the truth table by going to project, analyze circuit. Okay. Otherwise, you can go to window, combinational analysis, and you can check the truth table out here. Go to window, combinational analysis. You can check the truth table here, and you can find the expression for X, Y, and Z. You can find the minimized expression found using K-maps in both sum of product and product of some forms for different outputs. Cool. You can export table, build circuit directly, or do whatever you want. Okay. So this is circuit. Try building it on your own. Post the session. Now, yeah, that's it. Okay. There's one small part left. Sequential circuits. So what are sequential circuits? Sequential circuit is basically a combinational circuit with a memory element. Okay, so what's the difference between a sequential circuit and a combinational circuit? Is that, as I said before, combinational circuits outputs depends only on its present inputs. It did not have any memory elements. But in case of a sequential circuit, it has memory elements which stores its outputs, and its inputs are not just its present inputs, but also its previous outputs. So a sequential circuit's outputs not just depend on its present inputs, but it also depends on its previous outputs. So sequential circuits are very common. They're very important in digital design. So you'll learn more about it. I'm handing it over to Aruna now. Are there any doubts?
Yeah.
Aruna, you can continue now.
Yeah, okay. 1 minute. Can everyone see my screen? Yeah, Kartika, is my screen visible?
Yada, your screen is visible. Your voice is also
Okay,
audible.
okay.
Continue.
Fine. So yeah, we are going to continue with sequential circuits. So whatever Kartika said was right. Like it's a combinational circuit, but it will have something called as memory elements included. So you can see in this diagram. So if you see this memory element, it has like the previous outputs or inputs from the combinational circuit, right? So we should, if we include the memory element to the combinational circuit, then it becomes a sequential circuit. And then yeah, memory elements like those have two stable states. Like they maintain stable information. And then we have two types of sequential circuits. Those are synchronous and asynchronous. So moving on to asynchronous. So asynchronous means it, if an input is given to the memory element, it responds immediately. So you can see whenever this input is given to this memory element, it just responds after it. So if we move on to synchronous sequential circuits, then we have to know about clock signal. So clock signal is basically the periodic train of pulses. So it will be like equal amount of time, like it will be high and low in equal amount of time. So whenever this signal is high, the circuit will be on. So basically it responds to the inputs only at discrete time intervals. That is only when the clock signal is high. So these are the differences between synchronous and asynchronous circuits. So let's see in detail about the memory elements. So what are memory elements? So these store only one bit of information, either 1 or 0, and has two stable states. So there are two types of memory elements, latches and flip-flops. So first we'll see what is a latch. So this is the diagrammatic representation of a latch. So we give an input and the output will be produced. So we'll be seeing it in detail. I'm just telling the like basic understanding of it. So a latch responds to input level change immediately. So that means it's an asynchronous type, right? So this is about latch. And then as an add-on, like we'll be moving into gated latch. It's just an add-on of what is a latch. So basically it becomes functional based on the control input. Like if you see the diagram, when enable is high, then only the input will be like taken. Then only the gated latch will respond to it. Yeah, that is the difference between latch and a gated latch. So if the enable is equal to clock signal, then the asynchronous type will be converted into synchronous memory element. So yeah, these are level triggered memory elements. So let's see what is level triggering. So level triggering is whenever this the clock pulse is high. That means in this interval, like in these three intervals, then the latch or gated latch will be triggered. So that is called as level triggering. So we can see an example here. Like this is the input pulse, this is enable, and this is output. So whenever the enable is high, then the input is taken and it is shown in the output. So whenever it is low, it retains its past state. And again, whenever the enable is high, the input is taken. And so on. So I think you got a fair idea about it. Then next we move on to flip-flops. So there is only one difference between flip-flops and gated latches. So that is this clock transition detection circuit. So let's see what is it. So if you see this pulse, these arrow marks indicate rising edges. So in the previous case, it was level triggering. That means whenever this is high, the gated latch will get triggered, right? So in flip-flops, whenever it encounters this rising edge, then it will be triggered. So only that is the difference between flip-flops and gated latches. So yeah, clock transition detection circuit, it will detect rising or the falling edge of the clock signal. Yeah. So let's see what is edge triggering. So this is positive edge triggering. And the next thing is negative edge triggering, that is in the falling edge. So let's see an example for the rising edge, that is positive edge triggered flip-flop. So whenever it encounters a rising edge, the input is like here 1. So in the output also it is 1. And then in this space, it will not get triggered, right? So it will remain 1 in this entire time. And again, if it encounters a rising edge, here also the value is 1. So it just continues over here. And then here in this rising edge, it encounters a 0. So then it will move on to 0. And then similarly for negative edge triggered flip-flop, it just encounters the falling edge. So if you see, like both flip-flops and gated latches, you will see flip-flops are like more continuous and there are no discrepancies. Like here you'll see the alternating value is like it's not stable, but in flip-flops it is almost like stable. So we prefer flip-flops in circuits. Yeah, so let's see what is an SR latch. So before that, I'll just tell about the NOR gate. Like you guys will probably know before, but I'll just remind. Like in the NOR gate, if you see, if any one of the input is 1, then the output becomes 0. So I just told it to keep in mind, like we'll be using it. So let's see this working. So this diagram is the representation of SR latch. So we'll be going like deep into the working of it. So yeah. So here the S represents the set state and R represents the reset state. So here in this thing, Q is the output of this latch, SR latch. So if we see, we have constructed it using 2 NOR gates with crisscross coupling. Like, so it has 2 states like set and reset. Let's see what it is. So if set is 1, like if we give set pulse as 1. So as I said in NOR gate, whatever, like any one of the input is 1 means the output will become 0, right? So this 0 will be again transferred here. And assume like if it's set state, then R is also 0. So if 0 and 0 is occurring here, then here if assume that Q is initially 1, then also like it will become 1 only. So even if Q is 0 initially, due to this action, it will become again 1. So we can tell that whenever the SR latch encounters a set state, then irrespective of the previous inputs, the Q will remain only 1. So yeah, we'll move on to the next reset state. So assume that this Q is 1 initially, like this is the past state. And then we'll give the reset pulse as 1 and set as 0. So now this will become, this NOR gate will become 0. And the same 0 will be carried on here. And this will become 1. And since this is the complement, then Q will also change to 0. So whatever may be the past input or output here, it will convert it into 0 in case of reset pulse. So yeah, what happens when we give both 0? So assume that we have 0 here initially. Now if we have 0 here initially, this one becomes 0 here also. So this one here becomes 1, right? So we get again 0 here. There is no change in the input. That means it retains its past state. Okay, we'll check with 1 also. If it retain its past state, like it should retain 1 if it's in 0 and 0 case. So assume Q is 1 initially. So this 1 will get transferred here. So that means this will become 0. So again, if you see if R and S are 0, then we again get 1. So that means if Q is initially 0, then it retains 0. If it's initially 1, it retains 1. So this happens when R and S are 0 and 0. So let's see what happens if it's 1 and 1. So assume initially it has 0. Okay, we no need to assume. See, here anyways it's 1 and 1. So we'll be getting 0 and 0. But this is not possible, right? Like Q and Q bar are its complement. So we can't get 0 and 0. So this case is like forbidden. So we don't use that particular case alone. So you can check the truth table here. You can check the truth table here. 0 and 0, it retains its previous state. If set pulse is 1, then the next state, irrespective of the previous state, the next state will be 1. And if reset is 1, irrespective of the present state, the next state will be 0. And 1 and 1, nothing. Like it will be forbidden. That case is forbidden. So this is the diagrammatic representation of SR latch. We can represent it as this diagram also. So next we move on to gated SR latch. So gated is nothing but an add-on to SR latch. Like we'll be adding an enable here. So let's see how it's added. So we require 2 AND gates here. See, whenever this enable is 1, then only this AND gate will be activated and it moves on to this SR latch. So if enable is 0, then S and R will automatically become 0 and it will always retain its present state. Like it will not change into any other state. So that is one add-on here. So yeah, next is SR flip-flop. So I told you guys what is a flip-flop before. So we can put what is the change, like already I have told you. You can put it in the Q&A section. Like I want you guys to tell where we'll get the difference, like from gated SR latch to SR flip-flop. Yeah, clock almost like near. Yeah, so we'll be including this clock transition detection circuit. So that it will detect the rising or falling edge and it responds. So you can see this is the positive edge triggered flip-flop. So here is one triangle kind of thing. That means it is positive, like positively triggered. And this is the diagram of negative edge triggered flip-flop. Here we have a knot over here. So this represents negative edge triggered flip-flop. Yeah. And then, so in this SR latch, we encountered this case, like the forbidden case. So in order to avoid that, we can extend it to JK flip-flop. Like what if we connect this Q to J and Q bar to K? So we'll be like, I'll explain. So initially, if these two are zero, sorry, these two are one, then S and R would be one. So now it depends on the input or output of Q and Q bar. So it will depend on Q also. So that means we won't get that forbidden case. So let's see how it works. Like assume it is in enable, like this is one, the clock transition is like the clock is one here. So if we take this set state, J is 1 and K is 0. Automatically, if here it is 0, then it will be 0 here. And then yeah, if we assume Q to be 0 here, then this will become 0 here. So that means it just retains this 0. We get 0 and 0 in SR in this SR flip-flop. So it retains 0. So if it is 1, if J and K are like J is 1 and K is 0, then here it will become 1 and here it will become 0. Yeah, so now it is in set state. So it will be the JK flip-flop will set to 1. So yeah, we'll see that 1 case. So let's see what happens when both are 1 and 1. So assume initially Q was 0. So we get 0 over here. So if Q is 0, then Q dash is 1 here. So we get 0 here and 1 here. Right. So this is in reset state. Yeah, 1 minute. Okay, I have the delay. The JK flip-flop here is actually wrong. So I made a hypo here. So 1 second. So this is supposed to be Q bar. And this is supposed to be Q. Now we'll get the required thing. Okay, so now if you see in this 1 case, so if Q is 1 here, then this one will become 1. And automatically this one will become 0. That means it will become set state again. I mean, wait. Oh yeah, set is 0 and reset is 1. So this Q will convert it into 0. So that means toggling action will be taking place here. So if we see, if initially it is 0, then here it will become 0. Then here it is 1. So it will become 1 and 1 and 0 here. So it is in set state. So now Q will turn into 1. So basically 0 goes to 1 and 1 goes to 0. So this action is called toggling. So whenever JK flip-flop is 1 and 1, like the J and K are 1, then it toggles the previous state. Yeah. And you can see the diagram of JK flip-flop. And next flip-flop is T flip-flop. This flip-flop is only used to toggle. So that is the J and K are connected. So T can be either 0 or 1. So JK will be 0, 0 or 1, 1. So basically the truth table will get reduced. So whenever this T is 0, irrespective of the present state, the next state will become like it will say store the present state. And if the toggle is 1, that is the toggle value is 1, then it will toggle the value. If we give 1, then the T flip flop will be giving 0. And if we give 0, then it gives 1. So let's see the characteristic equation of T flip flop. So we'll be using T flip flop here. So let's see about it. So what is a characteristic equation? It is the representation of Qn plus 1 state in terms of Qn and T. That is a representation of the next state in terms of the present state and the toggle value. So we'll be building a truth table over here. So the present state is 0 and the toggle value is 0. That means it will be remaining the same. The next state will also be 0. So if it was 1 and 0, then it will become 1. So whenever this toggle is 1, so it will just toggle the input. Like if Qn is 0, then Qn plus 1 is 1. And if it's 1 and it's 0. So we can use K-maps to get the equation. So I think I don't need to explain this K-maps. So we get this equation over here. So basically it converts into a XOR gate. That is Qn plus 1 is equal to T XOR Qn. And it can be like T is equal to Qn plus 1 XOR Qn. So that's a property. So yeah, we are done with the theory part. So yeah, you can see the diagram of T flip-flop. We'll be using this. We are done with the theory part. So we'll move on in building a synchronous 3-bit up counter. So here we'll be making a counter in Logisim. So let's see the steps for the for designing the synchronous counter. So yeah, wait. Till now, anyone have any doubts? Yeah, flip-flop is more stable. Okay. If anyone have doubts, you can put it up in the Q&A. If you are clear, you can put a thumbs up or something. You can react with a thumbs up. Or else I'll explain any one of the flip-flop. Yeah, application will be seeing it now. Like we'll be using flip-flops to design the counter. So I guess I can proceed with designing the counter. Okay. So yeah, first step is finding the number of flip-flops and selecting the type of flip-flop required. So what do you think the number of flip-flops will be here? It's a pretty simple question. So we are designing a 3-bit up counter. So the answer is in the sentence itself. So how many flip-flops will we need? Yeah, 3. So we'll be requiring 3 flip-flops as only one flip-flop will only store 1-bit memory. So since it's 3-bit, we'll require 3 flip-flops. And we'll be using T flip-flops here. And the second thing is drawing the state diagram. So this is the state. So the state diagram means we should be drawing the next states and previous states. Like we'll be counting from 0 and it goes to 1 and 2. Yeah, and 3 and so on. So this is the state diagram. And state table, I'll be explaining it next. So, and then the next step is finding the expression for each flip-flop using K-maps. So we'll be using the expressions. Yeah, since it's a synchronous counter, we'll be requiring a clock signal and it should be connected to all the flip-flops simultaneously. So based on that expression, we'll be drawing the logic circuit. Yeah. So let's see what is a state table. We have present state, next state, and toggling value. So we have 3 flip-flops, right? So we can name them as TC, TB, and TA. So TC, we can store the most significant bit, and TA, we can store the less significant bit. So let's see what is present state. So this is the present state of the flip-flop, and to what we should convert it. Like we are writing to what it should be converted. So we'll be representing it the next state as plus, like QC plus, QB plus, and QA plus. So initially we'll be in 0, right? So we have to move from 0 to 1. So present state is 0 and the next state will be 0, 0, 1. That is 1. And similarly 1 to 2 and 2 to 3 and so on till like 7 and 7 to 8. Yeah, we can go only till 7 because it's a 3-bit counter, right? So yeah. So how to determine this toggle value? So there are 2 ways. We saw the characteristic equation, right? So we have the expression like the relation between the next state and the toggle value. So basically it's a XOR, like XOR of QC and QC plus will give TC. We can do in that way also, or else we can just say like if QC is here 0, like let us take the first case. If QC is 0 and QC plus is 0, that means the flip-flop has saved. The flip-flop should retain its memory. So that means the toggle value must be 0. And for QB also the same thing. If you go to QA, it just toggles from 0 to 1. So that means the toggle value must be 1. So similarly for the next thing. So 0, 0, that means TC will also be 0. If QB is 0 and QB plus is 1, then TB will become 1. Since the value is changing and so on. So you can determine this toggling values like that. Then yeah, the next step is finding the expression for this toggle, like the toggling values. Like we only have the state table, so we have to find like what gates to use and the things like that. So we must have a expression kind of thing, like TC is equal to QC into QB, something kind of that. So we'll be requiring a Boolean function to build the circuits. So let's design for, so this is the K-map for TC. So if you look into it, you can see in TC, this term, this is I think 0, 1, 2, 3. Yeah, M3 and M7. So both are 1. So we'll be filling 1 and 1 here. And yeah, just using K-maps. So this is QB and QA. TC is equal to QB and QA. And for the next thing also, we can similarly write like 1, 3, 5 and 7 are 1. So we can group it. And for TC, since all are 1, you can just say for any value of QA, QB, QC, TA remains 1. So the logic will be 1. So yeah, we'll be building this in Logism. So everyone can try it now also. I think my screen is visible. Katia, can you confirm?
Yeah, your screen is visible, Aruna.
Okay, fine. Yeah, we'll be designing the flip-flops. So here in the memory, we'll be having the T flip-flop. So we can just put it here. Like we require 3, right? So 3 flip-flops. And then we require a clock. So we'll go into this wiring. You'll be finding a clock over here. You can just put it here. So this is the clock connection. So it should be same for all since it's a synchronous counter. So next, so in that expression, we can see TC is equal to QB into QA. So that means we require an AND gate. So yeah, first we'll label this flip-flops. So this is C and this is B. This is A. Yeah. So this is QC, QB and QA. So we require an AND gate. We can just put it over here. So we'll connect it to TC. And I think, yeah, TA is connected to 1. So we'll take a pin over here. We'll connect it here, 1. And we'll make it as 1. And TB is QA. So we should just connect TB and QA. Yeah. Yeah, I think it's correct. So yeah, now we'll put the output pins. Okay, let's see if it's working. Yeah, so this is 1, this is 2. Yeah, it's working. Fine. So 3, 4, 5. So we have built a counter here. So this one is a simple counter. So we can level this up also. Yeah, I think everyone was clear with the simulation. Yeah, we'll see one more case. Yeah, 1 minute. We'll be using 4 variable K-map in the next counter.
Aruna, are you presenting anything?
Yeah, 1 second, 1 second.
I guess you didn't share your screen.
Yeah, I'll be presenting. Wait. Yeah, so now we can just do a random counter. I think the attendance link has been put up in the Q&A session. So we'll do 0, 2, 3, 5, and 8, some random numbers. So we'll just check what happens. So since 8 is here, that means we are moving into 4 bits. So we'll be requiring a 4 variable K-map. So let's see. So for the state diagram, yeah, here we will be initially going from 0, then 2, 3, and 5. And then, yeah, 8. So I'll just tell, you have to fill it out here also. So 0, 0, 0, yeah. So the next state will become 0, 0, 1, 0, right? So 0, 0, 1, 0. So you finally you guys have to tell me the equation. Yeah, you guys also can write out parallelly. So tell me the equation for TD, TC, TB, and TA. Yeah. So that's your task right now. Yeah, Kartika, let me know if someone puts answer.
Yeah, sure.
Yeah. So I have completed like the tables. So if you guys have completed the K maps, let me know. So guys, if you see, we are leaving few states, right? Like one we don't consider, and three, oh, I think three is there. So four we don't consider. So those are called don't care conditions. So in K maps, you can represent it. So we'll see the T, like I'll do one K map, so you'll be able to do the other. So if you see for D, M0 is 0 and M2 is 0. And M5 is also 0. Okay, sorry. M3 is 0 and M5 is 1. And M8 is also 1. So the other boxes, we have to fill it as don't care conditions. So that means we can put X, like other states, we don't care, right? So, yeah. So we can erase this 0 terms. So now you can group it. So now if we group it, we'll be getting TD as, like, yeah, you can tell. Yes. when you're not getting.
இப்ப நான் மறுபடியும் அவங்க பண்றதுக்கு என்கிட்ட எனக்கு கேக்குறீங்க.
So if you do the K-map things, you'll be getting TD as QC plus QD and TC is equal to QA and TB is equal to QA QB plus QC complement, QD complement, QB complement and TA as QC plus QB QA complement. So I'll be sending this in group also, so you guys can check it out. And yeah, the task is to implement it in Logism. Yeah, I hope you guys got some understanding of flip-flops and counters. I think you guys can leave like after filling the attendance form. If you guys want to ask doubts, you can also ask. Yeah, if you have doubts, you can put it up in the Q&A section. Yeah, you can leave. If you have any doubts, you can tell.